Hello, welcome to Predictive Modeling of the Data Center Lifecycle. This presentation is about the biggest challenge facing data center operators today, which is identifying, quantifying, and managing the risk that comes from operational flexibility in the data center. We will talk about the risk in the data center, a familiar story, the cause of risk in the data center, how to quantify risk scientifically so that better decisions can be made, predictive modeling, which is a solution to quantifying risk in the data center, and a case study. So let's take a look at a familiar story about how risk is incurred in the data center. This is a typical enterprise data center. It has been designed around an IT loading assumption that is a best guess at what will actually be installed in the facility. Assuming an IT configuration up front enables the data center system to be designed so that the IT configuration utilizes space, power, and cooling resources in unison as it is built out. This is the same data center now on the right on day one of operation. As it fills out, operational guidelines such as hot aisle, cold aisle, blanking, cabinet power limits are mostly adhered to, but the operator has the freedom to select and configure IT hardware in any way they deem necessary to meet business requirements. In this sense, they expect operational flexibility out of the data center, and this freedom leads to IT configurations that were never anticipated during the design process. As a result, health problems appear at 60 to 70% of full capacity, and this introduces risk into the equation. So specifically, the risks include hotspots and potential for circuit overloading that threatens IT services. It also impacts the data center's ability to hold a full IT load. Typically 30 to 40% of the IT loading capacity potential of the data center is lost. And these two problems force the operator to over-provision resources to make up for local shortages of power and cooling that threaten IT hardware. Let's look at the cause of risk that comes from operational flexibility in the data center. The computer game Tetris is a good metaphor for how risk is incurred by operating the data center flexibly to meet the changing IT requirements. To illustrate, we will play two versions of the game. As the games are played, the bar graphs at the top will track the space being used by the blocks. For the first game, we know up front all of the blocks that will be used. Knowing the blocks in advance makes it possible to arrange them so that the space on the Tetris board is used efficiently. This is similar to the assumptions that are used to design data centers. Next, we play the real game of Tetris, where the blocks are different from the design and unknown until they appear ready to be placed. The random changes from the design assumptions and the time pressure to place the blocks makes it impossible to use the space as efficiently as the design intended. In other words, freedom to break the design assumptions in real time, which is what we are calling operational flexibility, will fragment and eventually strand space on the board. And this prevents all of the blocks from being installed. This is called the Tetris effect. The Tetris effect applies to the data center. On the left, the IT loading configuration and sequence is known up front for the purposes of design, and under this assumption, space and power utilization as the IT configuration builds out is perfect. On the right, the design assumptions are broken by the IT configuration, and like Tetris blocks, the IT equipment will fragment the distributions of space and power. Eventually, the options for deploying IT equipment will run out before space and power does. This strands resources and exposes IT equipment to failure conditions. In the typical enterprise, colo, or government data center, 30% or more of the IT resources will be stranded by the Tetris effect. And this is a huge waste of capital. But even worse than stranded capital is the fact that IT equipment is put at risk by resource fragmentation. So you can imagine this unit being installed and tripping a circuit breaker because the power distribution had become fragmented and unavailable to this particular deployment. So is there a solution to this problem? Well, many believe data center infrastructure management or DSIM tools can solve this problem. So let's take a look at this. DSIM tools can track space and power as a function of IT build-out. This is possible because there are no losses of space and power as they are provided by the facility to the IT equipment. And this makes it possible to calculate space and power availability at any point in time by keeping good records of IT deployments and power used. So in this example, we can use DSIM to determine space and power availability before installing the unit. And DSIM informs us that power is unavailable in the left cabinet and space is unavailable in the right cabinet. We must move power to where there is space or vice versa. So we move power from the right to the left cabinet, and this should enable a safe deployment. Or does it? To complicate matters, IT equipment need cooling as much as they need space and power. So let's try this deployment again. But this time, we will observe the IT unit temperatures as the deployment is made. After installation, the IT unit that was deployed is fine, but the bottom unit in the cabinet next door loses its cooling. So this shows an aspect of cooling that is different from space and power. Space and power are directly coupled to IT equipment, and there are no losses of space and power between supply and the IT equipment. So fragmentation of space and power occurs only where it connects to the IT configuration, which is inside the cabinets. This makes it possible for DSIM tools to accurately track space and power availability as a function of the IT build-out. Cooling, on the other hand, is indirectly coupled to the IT equipment by airflow. Airflow can fragment anywhere, and often everywhere, in between the cooling units and the IT equipment. DSIM tools completely overlook this characteristic of the cooling distribution. But this is not the only problem. Airflow is invisible, it cannot be measured with sensors. DSIM tools with temperature monitoring can warn the operator that temperatures are rising, but they cannot show the cause of hotspots, which are airflow related. They cannot be used to fix the problem. More importantly, DSIM tools cannot be used to predict whether or not cooling will fragment as a result of a data center change. This means operators who rely solely on DSIM tools are perpetually one step behind the cooling fragmentation problem. And this puts IT services and long-term health of the data center at risk. The only way to predict and visualize cooling fragmentation problems is with computational fluid dynamics or CFD modeling that account for the individual units of IT equipment. The data center management process therefore must have an integrated set of space, power, and CFD modeling capabilities to address the risk from operational flexibility in the data center. So this brings us to predictive modeling. At future facilities, we call this form of predictive modeling the virtual facility. The virtual facility is a three-dimensional computer model of the physical data center at any point in time, past, present, and most importantly, the future. The modeling techniques combine modeling capabilities for space, power, and granular CFD modeling of airflow to predict the impact of changes to the data center health, the capacity of the data center, the availability of the IT equipment, the performance of the data center itself. This granular CFD modeling approach overcomes the problem of having to use non-physical and misleading modeling techniques, such as temperature trending. The virtual facility is used to quantify the costs and the risk of breaking the design assumptions, and this enables operational flexibility to the operator. It is also used to mitigate risk from operational flexibility at effectively no cost. So how do you quantify risk, or the Tetris effect? With the virtual facility, the level of performance at any point in time for the data center can be calculated. This is done quite often by design firms for the initial design of the data center. A data center must comply with 3 performance requirements as it's being designed. It must hold a specific amount of IT equipment, usually expressed in terms of kilowatts or megawatts. It must protect the IT equipment at all points in time from cooling or power failure conditions. And it must achieve these 2 things at a known and reasonable cost. So these 3 performance requirements together form the A score. They must be viewed together because they are interrelated, and the process of design involves finding the right balance between the 3 requirements. Operations is similar. As we saw, IT requirements will change. This will impact the ACE score. The operator must continuously recalculate ACE to quantify the risk that is being incurred by operating the data center in a flexible way. The ACE score is an output from the virtual facility model. So let's take a look at a case study in the application of the ACE score. This case study is from a global bank that is actually using a virtual facility to manage their data center today. They're using it to manage 20,000 square feet of Tier 4, very expensive, very mission-critical facilities that were commissioned in 2008, so they're relatively new. The facilities are being managed by a very experienced staff, and DSIM tools have been in place and in operation and used effectively since day 1 of operation. But despite having the experienced staff and the use of DSIM tools, these data centers were experiencing hotspots that they could monitor and measure and see in the DSIM tool, but had no visibility into the root cause of these problems. So again, when the data centers were commissioned in 2008, this was the A score for the design. This is the design intent of these facilities combined. Combined, they have a capacity potential of 3.5 megawatts. They wanted to operate these data centers at 100% availability. They could not afford any downtime of IT equipment. And they had a very specific efficiency goal in mind to try to achieve over the course of operations. When we got involved in 2011, that is when the baseline virtual facility models were created for these facilities. The calculation for ACE from the virtual facility models produced the following numbers. For capacity, the model showed that these 2 data centers together lost about 350 kilowatts of IT loading capacity. In addition, they were experiencing hotspots, as I mentioned, and they were affecting IT equipment, putting them at risk of failure. 3% of the total kilowatts of installed IT load was at risk of a failure condition. In order to even hold the data center at this level of performance for availability and capacity, they had to run their data center at a less than optimal level of efficiency, 74% compared to 100. After using the virtual facility model for 2 years and using the simulation and visualization capabilities to understand why hotspots were being formed, how the airflow moved through the room, why temperatures were what they were in the data center, they were able to increase the ACE score by a significant amount. In terms of capacity, they added 10% of total IT loading capacity from the baseline. They also removed all of the IT availability problems through the use of the model. And at the same time, they were able to increase efficiency from 74 to 81% over this 2-year period. To summarize, over a 2-year period after using the virtual facility model, to guide the operations of these data centers. They were able to reclaim 350 kilowatts of IT loading capacity, which was equivalent to about 144 cabinets of additional IT equipment they were able to install. They estimated the value of these cabinets to be about $10 million worth of capacity. At the same time, they were able to reduce their PUE by 15%, which gave them an annual savings of $1.15 million in energy and related costs. A detailed description of this case study is available from download from our website at www.futurefacilities.com. The white paper is called From Compromised to Optimized: How One Data Center Saved $10 million. Also available is a good description of the ACE performance score, which was written up by the 451 group, Andy Lawrence, and it was published in May of 2014. That report is also available on our website. Well, thank you for attending. We hope you enjoyed the presentation. We also hope you found it interesting and informative. Please email us at info@futurefacilities.com for more information, and we look forward to seeing you at a future presentation. Thank you again.